you sandwich an operator, if you want a position operator or a momentum operator or energy operator, you sandwich it between the wave functions. And just like I mentioned a moment ago, you operate, you multiply, and integrate. Now you would divide by this, but if we have pre-normalized and done this, this will be 1. But that's the formal definition, okay? So we'll take that. All right, now, we're ready to begin. Before we do that, we started with having a wave function that is a function of space and time. The space part could be x, y, and z, or it could be r, t, and v. We will see those, or we have a time part that goes along with that. In order to solve an equation, you have to break it up into the individual parts, then solve. You can't solve them simultaneously. So what we do is let the wave function, there's my capital psi, be equal to a space only multiplied by a time only. This can only happen under certain conditions. That is, that the potential energy is not a function of time. If the potential energy acting on the quantum particle is oscillating in time, like for example electromagnetic radiation, then you can't do this. So the potential cannot couple these things together. But in the absence, we say, all right, we have a stationary potential, then I can write it in this way. Now we're going to do a separation of variables. This is problem number 6. Problem number 6, I asked you to do this. You have psi as x and y, and you're going to break it up into a psi in x only and a psi in y only, multiply together. This is, again, under the conditions that any potential energy doesn't couple the x and y together. Okay? So if I had a potential energy of x plus y, that's good. But if I had the square root of x plus y, that's bad. That makes it inseparable. Okay? So under the case where no potential energy is complicating, that would be true. So what I'm going to do now is exactly what you're going to do here. In this, there is my time-dependent Schrodinger equation. What I'm going to do is make this substitution into here and here, and then write the result. On this side, I have the Hamiltonian. Remember, that's the energy operator. I'll put it at the operator now. Times psi times t, because I made that substitution. This will be equal to I h bar psi dt d little t. Because this is space only, the operator, the derivative of time isn't affected. Similarly, the Hamiltonian has only space parts. Okay? That means the t can come out in front. Now, in your homework, your Hamiltonian is going to look like this. You're going to have a Hamiltonian in x plus a Hamiltonian in y. That's the way you will break it up. So when you do h on psi x, psi y, make that x, for example, the x part, the y part can come out. Okay? And we'll see, we'll look back again at the form of that. But then you will do this. Once we have these things brought up, you divide both sides by your wave function again, or the product of the two terms, space and time. Okay? Since this t wave function, has been brought out front, you can cancel that with this. Over here, since the psi is not being acted on by the time derivative, that can go there. So what we have then is h psi over psi is equal to I h bar over t, derivative of t with respect to time. Okay? Now, space and time are independent of each other. Where you are doesn't depend on what time it is, or what time it is doesn't depend on where you are. So this says that I can manipulate this independently, and it still will be equal to this. There's only one way for that to be true. The only way this can be true, where I have all just space here, all just time here, and in your case, you'll have a x and a y. They're independent of each other, all right? But you're gonna find they will equal each other. You're gonna come up with this result. You're gonna have hx psi x over psi x is equal to hy sine y over psi. Well, you'll have something like that. Yeah, with a few little bells and whistles in there. Since these have to be equal to each other, yet are independent, they can only mean one thing. It is equal to a constant. So that means this manipulation, no matter what it is going to be a constant value. Manipulation of this, whatever it is going to be a constant value. Well, we already know what that constant is. On this side here, we have h psi over psi is equal to a constant. Well, that says that h psi is equal to a constant on psi. Well, we've already seen what that is. This is energy. So therefore, that there is your stationary state Schrodinger equation that we will be using the majority of the time. That's where we're going to begin today. When we get to radiation, we'll have to kind of go to this one. But then the other side then is equal as well. So we have then an IH bar, let me put it, over T, dt, d little t is equal to energy as well. Okay. Now, this one depends on our system, so we can't do anything with it just yet. But this one I can solve. Now, this is just a simple single derivative. I can do a separation of variables and get an answer. So for this, I can write that dt over t is equal to e over I h bar d little t. Right, t's on one side and the little t's to the other. I integrate indefinitely, so I have the natural log of t is now equal to e t over I h bar plus a constant of integration. All right? Manipulating to get the t, I have my answer. So t, which is now the time part, is equal to a e, and we will write it this way, minus I h bar t over minus I e t over h bar. Okay. Where this now is an undetermined constant. That's a e to the constant. E to a constant is just a constant. I combine it. Okay. And so this one would, if we stopped here, this would be our normalization constant. So we would normalize to make sure it is 0. But however, I'm going to combine it. So there's the t part. So now I can do this again and write that my total wave function now is equal to psi times now a e to the minus I e t over h bar. Okay?
Why did I end up in the?
I turned it. We had this as positive.
Yeah.
I multiplied by I and made that squared.
Oh, okay.
So I knocked that and made that negative. Just convenient to write that way. Okay, so when we want to use this time part to move our waves around, we'll have it. Okay? So this will be, you'll do a separation of variables and you'll just kind of show that you will get two of these, one at x and one at y. And you'll find that the energies add. So when wave functions multiply, energies will add. That's what you'll find out in 6. It's a simple one to do. Now let's turn to solving our first system. And then I'm going to walk you through very deliberately question 7. Because it's brand new to you and you want to see how this whole thing comes about. So I'm going to start with my stationary state. H psi is equal to E psi. And now these are the points of orders in which you're going to do things for every quantum system we see. So, all right, here's what you're going to do. You write down the system Hamiltonian, that's all the potential energies, all the kinetic energies, in terms of momentum. I'll do that in a second. Then you substitute it into the Schrodinger equation there, solve the differential equation, and then apply boundary conditions to get the undetermined constants. Okay? Now this first one is a little bit difficult because it is actually a particle in free space, nothing else is in the universe. Well, I'd like to see what the quantum says it's going to do. okay? So we first write down, or I'll make it a one-dimensional free particle, so that means I'm gonna have one momentum term. So I'll say that the Hamiltonian is equal to, and this is the energy, or the kinetic energy operator, is minus h bar squared over 2m times the second derivative with respect to x squared plus 0. That's the potential energy. It's field-free space. Okay, so it is a free space type of thing. So I have a 0 in here. I can change this. I can have an energy across the universe if I wanted to. We will take care of that later. So there is the Hamiltonian. That's the momentum operator, or I'm sorry, the kinetic energy operator. Potential is 0. Now, second point, substitute it into here and solve. So I write minus h bar squared over twice the mass. Now, second derivative of psi with respect to x squared is equal to e psi. Now, in your homework problem, I have given you a quantum particle on a ring. So imagine possibly a delocalized Benton ring. We have electrons that could be, they're a fixed radius, so they're circular around the ring. So in that problem, so I'm going to be very deliberate on going through this. Your Hamiltonian in there is provided. It's minus h bar squared. Since it's a rotating particle, it's 2I, where I is the moment of inertia. Okay? That's going to be mr squared when we finally get to it. And then second derivative with respect to theta. And you'll have a 0 potential energy on that as well. Okay? So what we're going to do here is going to parallel that perfectly. All right, so here now I need to solve this. What I will do is I will put this into one of the forms that we've seen. I'm going to multiply across by this, and I will have second derivative psi with respect to x squared plus 2me over h bar squared psi is equal to 0. So I subtracted e from both sides, give me a negative e. Then I multiply by this term here, which had a negative sign, so they gave me this. Conventionally, what we'll do is usually give this a value, we would call it k squared. It's squared because if you recall, when you have the solutions to this type of differential equation, it's always the square root of whatever's here. So calling that k squared is just convenient. So I now have a differential equation that looks like this, plus k squared psi is equal to 0. And that, of course, is one of the 3 differential equations I wanted you to know, because we're going to see it quite a bit. This, like those, we just simply write down the answers, and I write that psi is equal to, I'll have an a e to the I k x, notice the k becomes the square root, then plus a b e to the minus I kx. That is our general solution. Now, we now apply symmetry or boundary conditions. When you solve this, you should get an identical form. The difference being is that x, of course, is theta. Your k will have a 2i in it rather than 2m. Other than that, it's identical. All right, now, in this system, and you can use this argument in your particle on a ring system, this is an unbounded particle in space. And being unbounded, it's hard to have a boundary condition, you know what I mean? So I'm going to use an argument of just symmetry. What we're going to find later, this is part of that orthogonality that comes out of Hermitian functions. What we're going to find out later is that this coefficient here and this coefficient here give the probability of having this wave and this wave. Let's interpret this. I had mentioned that K has to have a unit of reciprocal distance. Essentially, it is a wave number. So a wave number multiplied by Planck's constant, so K times h bar is a momentum. So in a sense, K is a momentum term. It's in terms of wave number. If we want to get the actual momentum multiplied by h bar, we'll do that in just a second. So this is now interpreted as a particle traveling with a forward momentum. This is interpreted as a particle traveling with reverse momentum. Since there is no force, there's a field-free space, there is no reason to believe that there would be any likelihood of the particle moving forward or backwards. So by symmetry, which is a symmetry argument, and you can use that same argument on the homework system. You can have a circle, it's going to go around one way, and then you have another term that's going around the other way. Okay? But because there's no probability of one or the other, you just you do the symmetry thing like this. So by symmetry, then I just write that A is equal to B. So I can now bring my wave function as being equal to A, then e to the I k x plus b, plus e to the minus I k x. So there's my wave function. And again, the probabilities over the entirety of the universe makes it difficult to normalize. So we're kind of stuck with this one right here. But it's an unrealistic system because obviously there are other things in space. But that brings our system to bear. A couple of things we want to look at. First off, our k squared was equal to 2me over h bar squared when we put that together. Yours would be 2I over h bar squared, obviously. So that tells us that the energy from that system is k squared h bar squared over 2m. Note the similarity to p squared over 2m, which was the kinetic energy expressed in terms of momentum. So my argument then comes again, that k h bar multiplied together is the momentum. Okay, where k is now a wave number, so it's momentum squared over 2, exactly what that is. This system is not quantized. Yours will be, and I'll explain why. This system is the only system that is not quantized because there are no boundaries. Boundaries in quantized systems come about when you put a limit or put a boundary in place. I always use this analogy of a rope. If I wiggle the rope all in front of me, it'll wiggle any way it wants to. As soon as I attach one end of the rope to the wall, you get standing waves, right? You're limited. So wave functions, the waves of these matter waves, will do the same thing. But let's do something. Let's go to a couple of our operators and use them.
So energy is not quantized?
Not in this instance.
In a boundless system?
In a boundless system, so quantized states come about when you put limits on a wave. This is an unlimited wave. We didn't put anything else in space, so it is non-quantized. This is the only one you will see that will be like this. The homework one will be bounded, so we'll have to see about how that's done. So anyway, just don't want to run a couple of operators on this. Let's do let's say the Hamiltonian on side, just see what this works out to be. So this is, again, minus h bar squared, twice the mass, times second derivative with respect to x squared of, now this a e to the I kx plus e to the minus I kx. Note, by the way, that, this is actually a cosine function. If you notice, by Euler's relationship. And so this ends up being, that's a cosine wave we drew up last time. So the cosine waves go over infinity. So we can interpret it one of two ways. It's either this cosine wave or two traveling waves going in opposite directions, which produce then an interference pattern which gives you a cosine wave. So a couple of ways to look at it. But let's do this. Let's do this derivative. So minus h bar squared over twice the mass. Now a first derivative, I'll go ahead and bring the a out for the moment. This will then become, I take the derivative I k e to the I kx minus I k e to the minus I kx. Okay, so let's take the derivative again. So minus h bar squared is a over 2m. Then I've got one more derivative, so that becomes now, I get this I k squared, which becomes minus k squared e to the I kx, because it's I times I, -1, so we get the negative come out. Then here, I'm gonna do it again, I have a negative I squared k squared, where, well, negative ik squared, so it becomes I squared k squared, or negative k squared e to the minus I kx. Well, if I take a negative k out of this, then this becomes, taking that out, I have now h squared a, let me do it this way, h squared k squared over twice the mass times the wave function back again. In other words, it's an eigenvalue. It tells me that I can measure that. It's something that I would be able to measure. Let's do one more that's simpler. Let's take just this leading term here and use the momentum operator. Going in on our momentum operator, let's say what that is. Our momentum operator is equal to minus I h bar derivative with respect to x. So let's operate on that. So for this, I will just take the first term, and we can do it again to the second term. But just doing the momentum operator, I'll say, well, what is minus I h bar derivative with respect to x of e to the I kx? I'm just leaving the a off for the moment. When I do that, I get this minus I squared h bar squared. Then I get this derivative k squared, right? I h bar, sorry. I get I squared h bar k, then e to the I kx, which comes out to be h bar k times the wave function back again. So in this instance, I get a constant k h bar, and that's the momentum as argued. So QED.
What happens when you have more than one dimension of space? Do we assume that all the dimensions of space are equal?
There's no reason to believe in field free space that it would not be. Yeah. So if I said do this in 3 dimensions, that's exactly what we're going to do. Is what we're going to, later, when we get back to this exam, we're going to take that particle and we're going to put it in our room. So now we're going to have an x, y, and z. And again, if we presume no forces pushing in either direction, we'll get 3 identical terms. The energies Ex, Y, and Z will add, all the psi X, psi Y, psi Z will multiply. Okay? And that's how we're going to produce our 3-dimensional or translational motion. Yeah.
Is that h bar k psi?
Mm-hmm.
Okay.
Sorry about that. So that's that h bar, that's the momentum then. All right, now let's look at yours, because that is the free particle. And like I said, it's about the limit of what we can get out of it. It's somewhat uninteresting, but at least demonstrates how that is done. Notice that if I place this operator on this term, I will get a negative kh bar. So 2 ways moving equal momentum, one forward and one in reverse. Now in yours, it has a little bit more of a complication to it because it is bounded. So in this, I first have you solve the Schrodinger equation to produce the general solution. You will do that, just as we did here, to be identical. Then I ask, what are the boundary conditions for this system? So here's what I want to talk through this. One, I just said we can make an argument based on symmetry, and we'll have those 2 terms. Because this is a circular system, okay, you can, if you elect, you're going to find out that since it's moving in a circle, you're going to have, let me do. I'll come back to that, because let's do something first. The other thing we want to look at is the requirements on the wave function. And for the postulate, the wave function must be continuous. Well, that will be, because you're going to get an answer that looks like this, and that's what I've given you in the homework. You're going to have an A, e to the I call it I in theta, and b, e to the minus I in theta. Okay? And your n squared will be 2I e over h bar squared. Now n, just like k, we haven't determined what it is, what those values are. But This isn't continuous, that's satisfied. It is finite, so that's satisfied. So there's no infinite, there's no discontinuity, so we're good there. Here's the one you need to know, single valued. Because we're in a circular system, where you have a circle coming back here, so here's my circle, and ultimately your benzene ring you're going to look at. My wave can't do this, just kind of draw an eye, how this looks. So I can take my wave, it goes all the way around here, goes all the way around here. It can't do this. You see? So here I have, that's double valued. So that violates the waveform. So we have to make sure that this is single valued. That is our boundary condition. It has to be single valued in this circle. We're going to do the same thing when we solve for the hydrogen atom. So the hydrogen atom, when it goes around its orbit, it has to be single valued. And that's going to produce quantum numbers just like this is about to, because it is now a bounded system. All right, so here is then how you state that boundary. For this system, we must have psi at theta must be exactly equal to psi at theta plus 2 pi. Okay? So applying this here, and again, let me just apply it to just this leading term, because we're making the argument. You'll see why I'll more clearly once I actually do that. So I have then that e to the I in theta must be equal to e to the I in theta plus 2 pi. Okay? The right-hand side can be broken up into e to the I in theta times e to the I in 2 pi. Okay, follow me? So e to the I in 2 pi must be equal to 1. All right, when is that true? Well, it's easy seen if I say this equal to cosine in 2 pi plus I times sine n times 2 times pi. In other words, apply Euler's criteria there.
And n here represents?
N is, we're just about to find out. That's why we're doing it. We're now applying boundary conditions to find out what that N will be. So I'm going to ask them, we now put these criteria in place, under what conditions is that right-hand side always equal to 1? I mean, there's no I here, so this has to always be 0. That has to always be 1. When is that true? Wait, what? What must N be?
0.
To satisfy? And 2, 3. In other words, in integer. We now have a quantum number. That's where the quantum number came from. So N, so N must be equal to 0, and I'm going to expand that even further. 0 plus or minus 1 plus or minus 2 plus or minus 3, and so forth.
Why is there plus or minus?
Because if I put in a minus 2 pi or a minus 4 pi or a minus 6, it still goes to 1.
So quantum numbers can be negative?
Certainly. Certainly can. However, when you look at this, now I can apply another argument. If N is plus or minus values here, and these N are plus or minus values, these end up being identical terms. So we can just simply write it as a single term. So our wave function now can be written as some normalization constant. I'll just take the A. So I'll take an A, e to the I in theta. Okay? So applying boundary conditions produces quantum numbers. That's where they come from. You're putting a limit on a wave. So here we have N determined, plus or minus 1. we now know the energy, I can get that from here, so now the energy becomes N squared H bar squared over twice the mass, or 2I. And then again, that's kind of a momentum term as well. Okay, so NH bar over 2I. The last thing we need to do is to determine that constant there. We do that, we're always going to have one left over. And that leftover one is going to be our normalization constant. So now I want to say, I want to make sure, or ask the question, what's the probability of having this wave anywhere on that grain? What's the certainty? We'll set that equal to 1. Probabilities in quantum mechanics are psi star psi. So we set that 1 is equal to A squared times an integral over all space. All space for our ring system is 0 to 2 pi. When we do a particle in this room, all space will be from that wall to that wall to that wall, ceiling to floor. And those will be our limits we'll put on there. So this then has psi star psi, you go ahead and write this, and then fill it. So this then becomes dx a squared. Now, of course, psi star is just complex. So we're going to have an integral from 0 to 2 pi of e to the minus I in theta multiplied by e to the I in theta d theta, dx. That becomes e to the 0 times integral 0 to 2 pi of e to the 0 d theta, which of course then just becomes 2 pi a squared. Because e to the 0 is 1. The integral of 1 from 0 to 2 pi is 2 pi. That's equal to 1. So now we know a must be 1 over the square root of 2 pi. Okay. So now we can write our wave function completely. We know exactly what it is. So our psi now is 1 over 2 pi square root times e to the I in theta. And now we can apply our energy operators or momentum operators and start massaging and finding values.
Is A the same, like constant, is it the same for every other molecule, or do they differ?
A is this value for, it turns out it's that value for a plane polar cyclic system. When we get to spherical, you've already seen what it is. It turns out being 4 pi.
Okay. Oh, so they're different.
They are different, yes.
So then are quantum numbers relative to each particular molecule itself?
I'll qualify that every system.
Okay.
It could be a molecule, it could be a particle, it could be a rotation, it could be a vibration. So whatever system we're looking at, the quantum number is going to be defined by the boundaries on that system. So when we do a rotating molecule in the next section, chapter 12, we'll apply this same rule. And that'll get us our rotational quantum numbers. Now you remember those, remember that N, L, M sub L, that sort of thing. Well, this is a rotating molecule, so N is not an orbit, an electron. So it's just simply a rotating molecule, so it's going to have an L and an M sub L. So we have 2 dimensions. We have theta and phi, so we're going to get 2 quantum numbers out of it. And we will get these by doing this for one of them. So you'll see it. So that's why this is the process. This is how you do this. Yeah.
Why did the term with the B in front of it go away?
There's symmetry. A equals to B.
Yeah, I made an argument that since n can have plus or minus values, and for that particular system, then I'm allowed to just take one term here, and it includes all the motions at once.
Is that why K can be squared? Is the reason why? You said 1 over the square root of 2 pi. Is that why you said K can be squared earlier?
Why change A to B? Or
over H bar squared would be K squared.
Right,
Right.
yeah, when we wrote down this differential equation, okay, with this, I did this. Let's look at this again. So now I have for this, H side is, oops, there you go. So we have this minus H bar squared, 2I, second derivative of psi with respect to theta squared is equal to E. Sound right? Rearranging this gave me d2 psi d theta squared plus 2I E over H bar squared psi equal to 0. Just doing that manipulation. Then I just took this term here and at convenience, I called it n squared. I could have called it n. If that were the case, this, your answer here, this would have been, n would have been the square root of that. But it still would work. There's nothing wrong with that, but it's just convenient to do that. So once you have done that, then once we now know what n is, by applying the boundary conditions, then I went back into here, rearranged it to solve for energy, energy's quantized. So that's the process. Okay? And then, so you just go through that and kind of rethink that, how that is, that's taken. I said, determine the quantized energy for the system, normalize the wave function. I just did your homework for you. But then the last part, but I want you to redo it, because I will be asking you to solve the system. The last part, if the mass were that of an electron, compute the energy required to promote the electron from n=1 to the n=2 quantum state. So now you'll do a delta. You can do that either directly or you can derive it. You'll have a delta E. When we get to spectroscopy, this is what we're going to do. We're going to have an n+1 squared H bar squared over 2I minus n squared H bar squared over 2I. All right? And that would give me a general from one end to the next. Something like that. But if you choose, you can go from 1 to 2. So you can make this as, so that would be 4 squared, 2 squared. 2 squared H bar squared over 2I minus H bar squared over 2I. So that gives you what, 3 H bar squared over 2I? So that's going from the n=1 to the n=2. So I just put the numbers in. Then I can derive it in that way. So here now, get your I, get the mass of the electron, I'm giving you a radius. That's obviously a constant now, a perfect constant. So you can produce that delta E, turn that into a wavelength, and compare it to the one I picked up for benzene.
So with this one, we were going from 1 to 2, and you just substitute 1 and for all of it?
Yeah, that's right, so that's right. For this, that's correct.
So do we need to do it the same thing for 2, subtract 2 to find the delta E? Where's the 2 come into play?
Where'd this come from?
I understand where that comes from. So we're moving from 1 to 2,
Correct.
but we didn't substitute 2 in there at all, right?
Well, I did here, but I didn't here. This is general, and that is exact. So here I put n=2 in here, n=1 in there, but here I just said, okay, what if I asked for 3 to 4? Well, then I can do a general.
It'd be 3, 1.
Yeah, so you'll get
4 squared minus 3 squared.
Yeah, so you'll have an n squared plus 2n plus 1 minus n squared all times H bar squared over 2I, right? I expand that out. And so that, yeah, so it'll be 2n plus 1 H bar squared over 2I. So again, if I put 1, where n is always the origin state. So if I put 1 in for this, I get the H bar. So that's what we're doing. We're going to be looking at where these peaks come from in an infrared spectrum or rotational spectrum. We're going to do this. We're going to produce these general where these peaks will find themselves. So it's going to be that process. So just produce a number out of that, get a calculated wavelength, and I think I've given you the absorption of benzene about 250 nanometers. You won't get a perfect number because this is a very weak model for a benzene ring and an electron, but you'll find yourself right over the magnitude. It'll kind of work for you. So anyway, that's it. You know all there is to know. That's about to be the start of quantum mechanics. So go through, again, particularly in this section, go find all those concepts. What does being a commutator mean? And what is the significance of it being zero or non-zero? What are just basic operator algebra? Concept of the Heisenberg uncertainty principle, where it comes from. Again, in your notes, you just do what I did, where you just take these, and change those up so you can see what they're like. There's a probability. So we had just consequences of taking a quantum approach, very frustrating, and also the math is much harder. So classical mechanics is easy. Quantum mechanics is hard. And we're going to find that it's going to be insoluble very rapidly. Okay? Oh, I got to say about that.
So our test is Friday?
You what?
Our test is Friday?
I think so, yes. So I'll get a web report on Wednesday. We'll do a review on Wednesday.
I took,
Is that right?